This is lecture 4 for chapter 1 for Math 302, and in this lecture I'll discuss the use of an integrating factor. The integrating factor is used to solve any linear first order differential equation. In this method you're going to end up with two integrals. If they can be evaluated nicely, then you will have a closed form solution for your problem. If they can't be evaluated, then all you can do is write the integrals and use maybe a numerical method to solve them. Okay, so we're going to end up with two integrals and hopefully we'll be able to evaluate them. So first I will derive the method. Basically, the method is based on three rules from calculus. The first is the product rule, and you know this rule pretty well. So if you have two functions multiplied together and you take their derivative, you hold one constant, take derivative of the second, hold the second constant, and take the derivative of the first. Okay, that's the product rule. Then if you have an exponent, if e to the something, and what's in the exponent is a function of time, you can use the exponential rule and the chain rule to evaluate that. So the derivative of e to the alpha t is e to the alpha t times the derivative of alpha with respect to time. I should have said alpha as a function of t, not alpha t. Okay? And then you have the fundamental theorem of calculus that integration undoes differentiation and vice versa. So those are three rules from calculus, and on these three rules we develop the method of the integrating factor. So here we have our linear differential equation, and we need to write it in standard form. So here is the standard form, and in the standard form the coefficient of the derivative, the first derivative here, is 1. So you have to do whatever you have to do algebraically to get it in this form. The reason is that we're going to pick off this p of t to make the integrating factor. So if I start with k e to the you have to write it in standard form. You've got to do this plus r over k y to the t equals 7, so you can identify r over k as p of t. It's pretty obvious. I just wanted to write that one more time as an example. So the next step is to construct what's called an integrating factor, and this is the integrating factor. We call it mu is e to the integral of this term, p of t dt, and you'll see why this works later. Okay, so that's your integrating factor. So whatever you have multiplying the y term, assuming this is 1, you integrate that and use that as the exponent of e. We're not going to evaluate it right now. We're going to carry it all the way through the solution. So we get to a bottom line containing those two integrals that I talked about. Then we use those in examples. You do not have to rederive the method every time you want to use it. So the next step is to multiply that differential equation by the integrating factor. So we started like this, dy by dt plus p of t y of t equals some q of t. And then we're going to multiply by that integrating factor. So we multiply this side by that integrating factor, and this side, just sneak that in here, by the integrating factor. Okay, and now I've written it out here. Remember, the integrating factor is e to the integral of p of t dt. So I'll highlight the integrating factor here for you. It's right here, put it in the middle here for a reason, and over here. So that's all I've done, is multiply through by the integrating factor. Okay, now I want to look at this term right here, and I'm going to recognize that if I took the derivative of the integral of p of t dt, I would end up with, by the exponent and the chain rule, exponential and the chain rule, times the derivative with respect to time of the integral of p of t dt. Okay, so I use the exponential rule, I use the chain rule, and now I'll use the fundamental theorem of calculus. Fundamental theorem of calculus is if I took the derivative of this particular integral, it's an inverse of each other, so I end up with p of t e to the integral of p of t dt. Hope you can see that. So if I integrate something, okay, let me write that a little bit better. If I'm taking the derivative, I will just say psi of t dt, I'm going to get psi of t back. Okay? And that's what I did. And so now I end up with what I have here. Here's my result of differentiating this, which shows that the term right here is the derivative of the integrating factor. So let me write that out a little bit more. Okay, so I have the integrating factor times the derivative plus p of t times the integrating factor times y. And by what I showed you previously, it's also in the lectures, the written lectures, this is the same as because I can replace all of this with the derivative. Right, so that's the first step. The second step is to recognize that this is the product rule, or the result of the product rule. This is the same as the derivative with respect to time of mu of t times y of t. Because if I did that, I would hold mu constant and take that derivative, then I would take the derivative of mu of t holding y constant. So this whole side reduces to this derivative. Okay? If I wrote that out using the integrating factor, that means that this whole side here is really so I can replace this left-hand side by this expression. Okay, so I've written it again right here, typed it up so that you can see it. Here's that left-hand side all coalesced into that derivative. This is a derivative of the integrating factor times the solution. And it equals the integrating factor again times q of t on the other side. Now I'm going to take the derivative with, or the integral with respect to time. So I integrate this. I have to sneak in a dt here. I don't think and this is integrated with respect to time. Okay, the right hand side I can do nothing about. I'm just going to write it e to the integral of p of t dt times q of t dt. Okay, actually, well, no, that's fine. But what about the left hand side? Again, by the fundamental theorem of calculus, I have a derivative. I'm taking the integral of it. I'm going to end up with it. It's really just inverses y of t. So you see how that worked out? By taking that particular integral and recognizing just the chain rule, the exponential rule, the product rule, and the fundamental theorem of calculus, you can back out the solution. Here's the solution right here. Of course, I want to be able to isolate it, so I multiply both sides by e to the minus integral pt dt. Again, I would not write this as dividing, although you can divide since it's never zero. It's not an issue. It's better to write like this: e to the negative integral of p of t dt times this integral of everything that you had before. That's a t, there's a q, and a dt. Okay, here are the two integrals that I talked about. One is this occurs twice, and the other is this one. If you can integrate those, if you can evaluate those, then you will have a closed form solution. If you can't, well, that's how it is, and that does happen. So here's a summary of the use of an integrating factor. You start with a first order linear differential equation and you write it in standard form. Then you pick off the coefficient function of y. This could be a constant, but you have to find that. From that you construct your integrating factor, which is e to the integral of p of t dt. Alright, and then you get a solution. This is the final form here for the method of using an integrating factor. You do not have to rederive the method all the time. You just have to evaluate these integrals. And I'll give an example of that now. So here's an example. This is a circuit. It's a series circuit that has an inductor and a resistor in it, and some kind of battery. And here's my inductor, and here's my resistor. Okay. And I want to find the current that's flowing around this circuit, and here's a differential equation that describes it. First order, I need one initial condition, so this is an initial value problem. I'm going to use the method of using an integrating factor, so I have to put it in standard form. And here would be the standard form. Okay? It might seem wrong to you to say, why would I divide voltage by inductance? But you just do it to get the solution. Okay, now I can identify the P of t that I need. And then I can use this sort of template right here. Okay, P of t is R over L. So here's the R over L. Okay, well, I carried it out already. What's the integral of R over L dt? R over L are constants, so that's just R over L times time. Right, so all this becomes R over L times time, and I put that in here. Remember, there's a negative sign out here. Becomes R over L times time here. V over L is just a constant. That's the Q. And now this integral can be carried out easily. So if I carry out this integral, I'm going to have, again, e to the minus R over L times time sitting out here. And in here I have, okay, by the, you can work this out, I'll have L over R times V over L, e to the R over LT with an L, plus some constant C. Okay, I'm kind of run out of space here, so I'll just kind of go up to here and use this space. These cancel, obviously, and when I multiply through, distribute through this e to the minus R over LT, it combines with the first one and becomes 1, but is still present on the other term. So I've got equals V over R, right, plus C times e to the minus R over L times time. And now we'll write C in terms of the initial condition. Here's my initial condition here. I don't want that C sitting there. I can write it in terms of the I naught. So I'm going to do that now. So let me write this solution again. I of t equals V over R plus that constant C, e to the minus R over L times t. And I have an initial condition based on time 0. So I put a 0 through this equation, and it's going to equal I naught. equals v over r, no change here, and the e to the 0 is 1, so this becomes c. I solve for c. C equals I naught minus v over r, and here is my solution for this differential equation. V over r plus I naught minus v over r, e to the minus r over l times time. And we'll analyze that, and I'll show you a graph of it now. So here's the solution again typed out, and we have two terms similar to the case that we did before for the first order kinematics. We have a steady state term, and that's the term that doesn't vary with time. Then we have a transient term, and it's a decaying, includes a decaying exponential. Okay, we eliminated one. We didn't eliminate one. There is one solution here that also satisfies this differential equation, and is the equilibrium solution. We didn't have to eliminate it because we weren't dividing anything, but let's look again at what it is. Here's the differential equation again. Okay. And now if I'm going to use this to show that this is the equilibrium solution, the steady state, I'm going to let the current be v over r. So if the current is v over r, then I have di by dt plus r over l times v over r equals v over l. Okay, which gives me di by dt equal to 0. And that is shows that it is an equilibrium solution. If you start at some current that is equal to the voltage divided by the resistance, then you're never going to change. The current's going to stay just exactly the same in that equation. And the behavior of the transients is also similar to the previous case. Here's the graph for that, the solution of several solutions for the series RL circuit that we solved using that integrating factor. This is the steady state or equilibrium solution right here. If you start greater, say at 4 times it, you're going to decrease towards it and asymptotically approach equilibrium. You'll never reach it and you'll never cross it. If you start less than it, with a current less than V over R, say at 0, you're going to increase to it asymptotically. I want to mention something about time constants. In the homework file, which has, in case you haven't looked at it, it has references to pages in the textbook that are similar to the topics I'm discussing, and also has some sample homework problems from the textbook. The textbook homework problems they're pretty good, and I've selected some of them. And one I selected right at first for lecture 1 is the whole use of time constants. I want to talk just a little bit about that if you're not familiar with it. If I have something to the base t, and I've got t over something, I'm going to call it tau, which really it's a half-life, and I graph this, say I start at 1, and here's time. Okay, every time I get to one time constant, I'm down by a half. Here's 2. I'm half of a half, etc. So if I count by time constants, all of the graphs, oh, that looks pretty bad. They're going to look the same and not at all like this. By the time you get to one time, sorry, maybe I'll try that again. So using the tools here a little bit better, I'm going to graph t to the minus 2 to the minus t over the time constant. If I start at 1, then at one time constant I'm down to a half, At 2 time constants, I'm half of a half, quarter. At 3 time constants, I'm down to an eighth. And if I connect these dots, I'm probably not doing any better job than I did before, which is typical of me. Okay, I get a certain curve. If I can then add, say the time constant is 5, then this would be 5, 10. If the time constant is 7, 7, 14, 21. If the time constant's 100, this is 100, 200, 300. So these are minutes. Okay, here's the actual value of the time constant, but if you graph in terms of time constants, it's all going to be the same. It's going to fall at the same rate. For most of these problems, we're having not the base 2, but the base e. So we have to do this a little bit differently. Okay, so it's going to be like this. And that's why I did select that homework problem for the first lecture. I selected a bunch of homework problems for you to look through, and that had to do with finding these time constants and thinking in terms of time constants. Okay, so what we have is e to the minus t over the time constant. So if I start at 1, I'm down to 36%. This is bigger than 2, so we have a bigger fall than 2. And that happens in 1 time constant. If I go to 2 time constants, then I fall into 36% of 36%, which is about 0.135. And so we're going to get a little deeper fall, but it's going to be similar. And again, it's similar no matter what the time constant is. So it's important to pick out these time constants. And you can pick them out if you have e to the minus, I'll say alpha t. Alpha is called the attenuation, which is sort of a misnomer because you can see the attenuation comes from the e. This is just how fast it's happening, right? And if you want to write it as a time constant, that would be 1 over alpha. It's a time constant because you have to write in this form to graph like this. Not multiplied, but dividing the t out. Here we're looking again at the solution that we obtained for this circuit, and here is the attenuation, R over L. So it's minus alpha, or AT, is attenuation, and that is e to the minus R over L times time. But if you want to write it as t over a time constant, then that would be e to the minus t over R over L, so that would be t times L over R. Okay, L over R is a time constant, tau. And here I graphed this. Here is time and time constants. Of course, it's increasing in a similar fashion if you start less than equilibrium, and here it's dropping. Okay, and then the actual time constants I put up here. Okay, so use of integrating factor applies to first order linear differential equations. They have to be written in a standard form so that the number multiplying the first derivative is 1. Then you look at the coefficient function, can be a function of time that's multiplying the function, the y of t, and you use that to construct an integrating factor. You don't have to rederive the method. Instead, you can use this following form. So you plug into this form here, and you hope that you can evaluate these integrals. And if you can, you get a closed form solution.